lateral entry students as well. Probably this is your first class
Yes, sir.
of numerical analysis. We have till now had 4 previous classes. So for that, obviously, you have missed out on the material. So what you can do is access the recorded lectures that were given. I have provided the links of the recorded lecture in the classroom. So you will be able to access those materials, as well as some notes and PDFs, and of course the uh, presentations and slides. So all of these are there in the classroom. Now it becomes your responsibility to sequentially access those, go through the material, listen to the lecture, and report back to me if you have any kind of problems. Okay. I have tried to
Okay,
explain
sir.
as much as possible in those lectures, but of course there might be certain issues, queries, doubts arising out of those lectures, and you are free to discuss with me. You will have my mail ID from which I sent you the today's class link. You also have my phone number, I think. If not, it is available with the class representative. And I would request Shattam to make the number available to them, so that you can contact me in any kind of, if you have any kind of questions. So that's all regarding the lecture materials. Obviously, from next week onwards, we have the puja vacation. So no classes for the next 2 weeks. Probably you will get the opportunity, if you want, of course, because it's after all puja vacation. So probably you will have plans, definitely, but don't waste all the time, all the free time you get in only fun and games, but allot some time for this these courses, not only the numerical analysis courses, because you are joining late. Probably 1 month, 1.5 months has already passed in this semester. So you will require a certain amount of extra effort to catch up to that level of whatever has been done in various different courses. So that's as far as the introduction. Today, we will be looking at something which is called regression or curve fitting, which is quite away from what we discussed in the last class, which was solution of nonlinear equations. So there we dealt with equations and its solution. But today's class is not exactly solution of equations, but trying to fit curves in given set of data points. By the way,
Sir,
any questions from previous
sir,
class?
sir, what about method of order of method, sir? আমরা যে মেথড গুলো করছি মানে ওটা অর্ডারটা কি করে ফাইন্ড করবো স্যার?
Order means
একটা আপনি যে বইটা বলেছিলেন ওটা একটা ইকুয়েশন দেয়া আছে স্যার, অ্যাসিম্পটোটিক কনস্ট্যান্ট দিয়ে।
are you talking about order of the errors?
না স্যার, অর্ডার অফ দি মেথড, যেমন নিউটন র্যাপসন মেথড ইজ অর্ডার অফ 2।
I'm not sure. Maybe I will just check up and I'll tell you later on. Okay.
Okay.
It might be that they are talking about the level of errors. Okay. Remember that I had shown you one Taylor series expansion, right? In that Taylor series expansion, while deriving the formula for the Newton-Raphson method, we are actually discarding some of the terms. Obviously, we are not taking into account the entire Taylor series, which goes up to infinity. So we are basically truncating that series after 2 terms. So whatever is left out is in the form of, it appears in the form of an error. And this error would be of because we are truncating after the linear term. So obviously from the quadratic term onwards, there will be errors. So the order of the errors would be maximum
ওটাকেই মনে হয় বলে।
epsilon to the power 2. So that is why maybe it is referred to as a order 2 method. Is that clear?
Yes, sir, but there is a constant asymptotic error constant. So how
Okay.
can you know the value, sir?
For that asymptotic value, let me check the book and what they are means talking about that I will let you know later on.
Okay, sir.
Okay. So any other questions? Okay. So one more thing is some of you have not yet submitted the two assignments, one assignment and one class performance that has already been given. So I would request you to complete that quickly and submit it at least by the end
স্যার
of this week. Yes.
স্যার বলছি মানে আমার আর কি অ্যাসাইনমেন্টগুলো এখনো সাবমিট করা হয়নি।
Okay.
মানে আমার একটু মায়ের একটু অপারেশন আছে, এই জন্য একটু ব্যস্ত আছি বাড়িতে, ঠিক
ঠিক
মানে
আছে, কোনো
পড়াশোনা ঠিক
প্রবলেম
পরিবেশ
নেই,
হচ্ছে না, একটু লেট
কোনো
হতে
প্রবলেম
পারে
নেই।
স্যার।
তুমি পরে জমা করো, কিন্তু প্লিজ সাবমিট ইট, মানে কারণ এগুলো পরে যখন
ইয়েস স্যার,
মার্কস
ওকে ওকে।
ট্যাবুলেশন হবে
হ্যাঁ স্যার,
তখন যদি তোমার এটা মিসিং থেকে যায়, অবভিয়াসলি ইউ উইল নট গেট দ্য মার্কস ফর
হ্যাঁ হ্যাঁ
দ্যাট পার্টিকুলার অ্যাসাইনমেন্ট। ঠিক আছে,
ঠিক আছে, আমি আমি
তুমি নিজের
যত
মাথায়
তাড়াতাড়ি
রাখবে
সম্ভব
কিন্তু,
আমি
ঠিক আছে?
সাবমিট করবো
হ্যাঁ,
ইনশাআল্লাহ।
নিজের
হ্যাঁ
মাথায় রাখবে, এটা কিন্তু সাবমিট করতে হবে যখন তোমার
ওকে
সুবিধা
স্যার,
হবে, যখন তুমি সময় পাবে তখন সাবমিট করবে।
ওকে
Also
স্যার, ওকে।
for the lateral entry students, obviously you are not expected to right away submit the assignments, so I will keep the submission portal open uh, for say substantial amount of time from now onwards, because you will have to first of all go through the material, listen to the lectures, then solve those problems. So you will require some time. Sohail, what you can do is you try to submit with the lateral entry students. Okay. So
ওকে স্যার, ওকে।
they will need some time, and as far as I understand, you will also require some time to
ইয়েস
cover
স্যার,
that, and that way I think we can deal with this issue. Okay.
ওকে স্যার।
Okay, sir.
So that's all regarding the say preliminaries discussions. Let us now go to the presentation. But can you see the screen?
Yes, sir.
Is it visible? Okay.
Yes, sir.
We start the recording, then we'll move. Welcome to this class of numerical analysis. Today we are going to be discussing about curve fitting through least square method. This falls under the broader domain of a subject or domain knowledge known as regression. In science and mathematics, as well as in the applied domain of engineering and technology, we often come across a collection of data points, which can be represented something like this table on the right hand side. So it has a column of x values, and corresponding to x values, each of the x values, there is a corresponding value of y. So x1 corresponds to y1, x2 corresponds to y2, like that. So from 1 to n, so n number of data points are present in this table. And these are all discrete data points. What is meant by discrete data points? If we take these data points to, let's say, an xy plane, we have the coordinate axis like this. We have x here and y here. What we'll get is a collection of points such as these. And these are x1, y1, x2, y2, going up to, say, xn, yn. It's quite clear from the plot that they are discrete in nature. There is no curve or smooth curve connecting all these data points. So what we have here is a set of discrete points scattered throughout the xy plane. The next question would be, how do we obtain such kind of data? Well, that can be attained through multiple, say, avenues. Maybe it could be an output from an experiment that you have devised. It may be some observations or measurements that you have taken. And obviously, these observations are made at, say, some spatial distances or temporal distances, meaning it could be spaced out in time or in the, say, one of the coordinate directions, or maybe both coordinate directions. For example, I can find out or observe or measure the velocity of a particle moving through in a medium. And I have taken these values, taken these data points at discrete time intervals. So at time t equal to 0, I have measured its velocity. At time t equal to 5 seconds, I have measured its velocity and tabulated it in such a way that it creates this table. So at t equal to 0, you have one velocity value. At t equal to 5, you have one velocity value. Like that, you will go up to certain time period and populate this table. Any questions?
Aranya is asking about the code of previous two methods, sir.
I did not get it.
Previous code,
Sir,
we have to code it, right? The previous two methods.
yes,
Yes,
sir.
yes, yes.
Complement. You have not
Yes.
seen. Yes, yes.
No, I
Sir,
have not
was
shown it.
wondering-
I have not shown it because
Yes, sir,
I have something in mind. Because I'm not going to be doing the code. You will be doing the coding, and that will be given in terms of an assignment. Probably that will be after the puja vacations, but it will be. It is there. It is in the syllabus. It will be covered.
Okay, sir.
Okay. So let us just come back to what we were discussing. So as I said, you may have devised an experiment in such a way that you find out the displacement of a particle moving through some medium at some discrete times. Time values such as 0, 5, 10, and so on. So those are absolutely discrete data points. There is nothing connecting those data points as in case of a smooth curve. So you do not know how in between those data points the system actually behaves. And of course, here you can very easily identify that one of the variables here is an independent variable. The independent variable in the example that I just now mentioned is, of course, time. And with respect to time, there is a dependent variable, which is the velocity. If you look at this table, you have a column of x's, that is xi, I varying from 1 to n, and the independent variable is x here. Whereas the dependent variable, which obviously is dependent on the independent variable, in some way or form, and that is the yi's, y1 to yn. What is the relationship between the two? It may be a monotonically increasing curve or a monotonically decreasing curve, or it might be a sinusoidal curve. Whatever be the nature, there is some form of relationship between x and y. Let us talk about another example, which would probably help us understand how this relationship between x and y, or you can say y and x, actually works. Here we have another set of discrete data points. How these are obtained? Let's say you have devised an experiment where you want to test the force displacement relationship of a spring. We all know what springs are. So let's say this is a spring with a weight pan attached at its free end, and you are putting certain amount of weight on this weight pan so that there is some displacement or deformation of the spring. It is going to be a downward deformation, and with the help of a precise scale, you are going to measure the displacement. You are putting force here, you are getting displacement here. So this can be considered as the independent variable, and dependent on that value of force, you obtain the displacement, which is the dependent variable. In this graph, on the x-axis, you have the applied force, and on the y-axis, you have the observed or measured displacement. And you can see that if you perform this putting of force and measurement of the displacement 100 times, you obtain 100 number of data points. We have a pretty clear idea about how the force, spring force, and the displacement varies. This is a linear relationship. And you can see that although this band of discrete data points are not exactly linear, but they tend to sort of indicate towards a linear relationship. If you increase force, the displacement increases proportionally. That is what this graph is actually showing us. So this is the functional relationship that we are talking about between the dependent and the independent variables. Now, what if I want to know what happens at points other than those for which the data has been observed or measured? You can say for which the data is available. Think of the previous two examples. First one, displacement and time. I have time data at 0, 5, 10. So these are discrete points. And the displacement data, or you can say, I was talking about, I think, velocity. The example that I had given, I had talked about velocity. So at times 0, 5, 10, these seconds, you have some velocity data. But suppose I want to know the particle velocity at t equal to 2.5 seconds. I have not measured the value at 2.5 seconds. So what to do at that point of time? What we can do is fit a smooth curve, construct a curve through those series of data points, and that would give us a mathematical function. Obviously, the graphical representation of the mathematical function would be the fitted curve. So here we can fit a curve through those series of data points. And once that curve is fitted, you have an idea about what would be the dependent variable value at certain intermediate points.
হ্যালো স্যার, এই তোরা কেউ
স্যার
স্যারের কথা শুনতে পাচ্ছিস? হ্যালো,
স্যার
বন্ধ হয়ে গেল।
ए सर को फोन लगा सत्यम सर को फोन लगा, सर प्रेजेंटेशन का ऐसे समझ नहीं पाएंगे कि उनका नेटवर्क चला गया है।
हाँ लग रहा है मेरे को भी। हाँ
फोन कर भाई, फोन कर।
फोन कर सर को फोन कर।
Can you hear me? Am I audible?
Yes sir.
Okay. I have a power cut in my home, so that's why the Wi-Fi went off. I have connected through
আবার শোনা শোনা।
হ্যালো,
can you hear me?
yes sir, yes sir.
Okay. I have joined through mobile hotspot, so probably the connection is not going to be that strong. Satyam was calling me, so
Yes sir.
yeah, I know because the disconnection is due to the power failure. Anyway, let's try with the hotspot. So, as I was saying, that if you obtain a curve that is fitted through those series of data points, then you have a mathematical function available to you. And with the help of that, what you can do is get values at intermediate points. The velocity can be obtained at certain intermediate points, say t equal to 2.5 or 3 seconds. Not only that, there is certain other advantages also. It becomes easier to apply certain mathematical procedures if you have a continuous function representing the data. For example, the velocity data can be integrated once to find out what would be the displacement, or the velocity data could be differentiated with respect to time once to find out what is the acceleration of the particle. If the function is not continuous, then obviously you have difficulties applying these mathematical procedures. But once you have, through those discrete data points, fitted a continuous smooth curve, then you can apply these integration or differentiation to find out various other different parameters. In fact, if you are able to measure the acceleration at discrete time intervals, then of course you can perform successive integrations on the available functional value or the functional representation, the mathematical function that you obtain. If you integrate it once, you will get the velocity. Integrate it twice, you will get the displacement. So these sort of procedures become more easier to apply if you have a fitted smooth curve. And that is the importance of curve fitting in numerical analysis. And there are two broad domains under curve fitting. One, as you can see here, is known as interpolation. This is where an exact fit to the data is required. Its counterpart is known as regression, which is the point of focus for today's class. And here, the focus is more on, it's more towards a statistical inference. Here you assume, or let us not say assume, here you presume that there are errors in the observed or measured data that you have got with you. That is, those discrete data points represented, such as this in this table, they have got errors in them. That is understood at the beginning. So how much uncertainty is present in a curve that is fit to the observed data with random errors? That is the focus of regression. The basic difference that I can put in front of you in layman's term is that in interpolation, you try to hit all the points. That is, in XY plane, those discrete data points are there. So you try to get a curve, a mathematical function that passes through all the data points. Whereas in regression, your objective is more towards finding out a best fit curve. So the concept of best fit is related to regression. It means that you may not be passing through any of the points in the XY plane, but what you obtain in the end through that curve is the minimum amount of error or deviations from those points. So that is the focus of regression. And these two, interpolation and regression, are very important in the field of numerical analysis. Let us now just go a little bit more in depth in trying to understand the fundamental differences between interpolation and regression. What is interpolation is explained in the first point over here. It says that if the value of a function fx is to be found at some point x dashed in the interval x1 to xn, and x dashed is not one of the tabulated points, then the value is estimated by using the known values at the surrounding points. And this procedure of finding out the values, estimating the values at the intermediate unknown points using the surrounding known values, is known as interpolation. Let us look at this explanation graphically. So we have the XY plane here. That is, say, one of the first points represented by x1 and y1. Similar to this, there are n number of data points in this XY plane, as already explained to you, and you can probably understand by now that these are discrete data points. We do not have any kind of idea what the functional value is at this moment in the intermediate points, meaning we know the value only at x1, x2, x3, x4, x5. Here I have considered n to be equal to 5 in order to keep the figure clutter-free for the sake of clarity. So we have these data points. Now the question is, if I have a point x dashed here, what is the y value? What would be y dashed? From the tabular data that I have, discrete data that I have, I do not have any idea of this. Whether this y dashed is somewhere here, or is it somewhere here, or maybe it is beyond that as well, somewhere here. Where exactly is this value y dashed? How do we get that? The way we can get that is through interpolation. What is interpolation? I have already explained once. And I will say it again, that the value of y dashed is determined on the basis of the known values. That means the known values around this point is these things. So depending on them, you find out the value of y dashed. For example, the simplest way that we can think of this is simply join the points here and here. That is the third and the fourth point through a straight line. If I join it through a straight line, then I have some idea of what this y dashed is going to be. So that is going to be a linear interpolation. There may be a quadratic interpolation as well, where I take up this third, fourth, and fifth point and join them through a quadratic curve. Or it may be considering the second, third, and fourth point and joining them through a quadratic curve. So that is a quadratic interpolation, nonlinear interpolations. Here, one thing is for certain is that these data points are assumed to be exactly known. Whether I use linear interpolation or quadratic interpolation or maybe even higher order interpolations, it is assumed that the points are known exactly. What it means is that it has good enough precision so that any errors, if present, would be of such a magnitude that it can be ignored or neglected. You can neglect the error. And once you have done that, think of a curve of some type. As I mentioned, it could be a linear one, considering only 2 points, or could be a quadratic one, considering 3 points, or higher order curves, considering more number of points. But you have to think of a certain type of curve that passes through each of the data points. Could be something like this. Obviously, this is a higher order interpolation, and it passes through all the given points. And once you have determined what this curve is, then it's quite easy to know what this y dashed is. Again, I would mention that there are different types or different kinds of interpolation, and they would probably give you slightly varying answers. This is a higher order interpolation, as I mentioned. Now, if I had joined these 2 points, that means the third point and the fourth point through a straight line like this. That would be a case of linear interpolation. And now, probably the value of y dashed would be slightly different. So, different interpolation formula would probably give you slightly varying answers. But I think the concept is pretty much clear that depending on the points around the unknown point, that is x dashed, you try to find out the value at the point x dashed. That is, the y dashed value needs to be found out. There is also another thing to consider here. We are talking about a point which is within the domain or interval x1 to xn. What if the point lies outside? This is the interval x1 to xn. Suppose the point is beyond this interval, somewhere here. If that happens, if the point lies outside the interval x1 to xn, then the estimation is called extrapolation. If the point is inside the domain, relevant domain, then we call it interpolation. If it is outside the domain, it is called extrapolation. There are certain problems attached to extrapolation as well that we will talk about when we deal with interpolation in much more detail. So the point that you should remember from this long discussion about interpolation is that in interpolation, the interpolating function passes through all the discrete data points. It hits all the discrete data points because we are considering that the errors are negligible. So the position of these points, discrete data points, are precise and accurate. And that is why the interpolating function passes through all those discrete data points. Now let's move to regression. We have considered the same xy plane and the same discrete data points x1, y1 through to x5, y5. But there is a difference now, is that previously we considered that these data points did not have any kind of errors, or errors, if any, were negligible in amount. But now we consider that the tabular values have some errors attached to it. There are some errors associated with the discrete data points. For example, if the table of values are obtained through an experiment, then there are bound to be some experimental errors. And what it means is that, suppose this point, its position in the xy plane could vary within this error band. Let's say this is known as the error band. Because there is some error, I do not know whether this x3, y3 is precisely over here. It might be somewhere here, over here, or it could be somewhere over here. It is quite possible that this error band could be very small, or it could be quite large. Depending on the type of experiment, how you are observing the value, how you are measuring the value, what is your measuring instrument, depending on all these factors, you may have a large amount of error or a small amount of error. Bottom line is that there is some uncertainty about these discrete data points. As already mentioned, due to that uncertainty, these experimental errors may vary over a range, and some of the errors might be quite large and some of them might be quite small. And you know that these sort of random quantities can only be described statistically. So there is a statistical inference related to the problem of regression. And in such a case, one can fit a curve only approximately. Suppose you are trying to fit a curve through these data points which have some amount of error. Now, can you just precisely say that I would like to hit all of these data points? You do not have any significance attached to it, because the position of these discrete data is variable. It could change. I should not say it could change. It could be anywhere within this error band. So what is the point of trying to pass through exactly that point? The better approach would be to try to obtain a curve which is statistically the best fit, which is going to give you the least amount of deviations or error. I can fit a straight line like this, which might be having the least amount of deviations from all the given points that contain certain amount of uncertainty, certain amount of errors. And you can see that these deviations are provided by these red dashed lines. There is a line over here as well, but it is obscured by the error band that I had drawn. But you can see the lines over here. So those are the amounts of deviations that is present in case of this fitted line. It's a linear fit, of course, but you have some amount of deviations from the given points. And needless to say here, you can quite clearly see that this fitted straight line does not pass through any of the given points. From all of these given points, it has certain amount of deviations. I can try to fit this quadratic curve as well, the green curve. It's not linear. It's not a straight line. Probably it's a quadratic curve. And that would be a nonlinear regression problem. Or I can try to fit something like this. But the underlying principle remains the same. That is, I have to try to minimize the amount of deviations from those given data points. And that gives you the statistically best fit curve. So here, the curve need not pass through all the discrete points. This is where it differs fundamentally with interpolation. In interpolation, you pass through all the points that are given because there are no errors in those points. But in regression, the curve need not pass through all the discrete points, which inherently have some errors associated with them. Okay, let's move forward and talk about linear regression. What is linear regression? It can be defined as the procedure for obtaining the equation of the best fit straight line that passes through a set of points. And that is exactly what is depicted over there graphically. You have a discrete set of data points. 1, 2, 3, 4, 5 points are there. And a straight line has been passed through all of these discrete data points, not hitting them, mind you, but with an objective of getting a best fit curve. As I explained already, here you try to minimize the error, the deviations from each of the data points that are given. So in the end, what we can say is that this straight line passes as closely as possible to as many points as possible. Obviously, if you try to draw a curve around here, somewhere in this region, that is not going to be best fit. It is quite far away from these different points. Or a line, suppose passing through somewhere here, that is not going to be a best fit. So there has to be a unique best fit line that one can determine. So this is again the same straight line and the same set of data points through which it has been fitted. And in this slide, you can see that the deviations D1, D2, D3, D4, and D5 have been marked out. So these are the deviations from those given points. Let's say the approximating function. What is the approximating function here? Obviously, this straight line. This straight line is represented by y bar. This is y bar, by the way. This is y bar equal to fx. And as it is a straight line, it can be represented by the given expression given equation a0 plus a1 x. From your concept of coordinate geometry, you know that straight lines can be written in this equation form. Now, what are the errors between the approximations? That is, those approximated values and the best fit curve. They are given by d1, d2, d3, d4, going up to dn, where n is equal to 5 here. And the expressions for them are quite easy to obtain. It is going to be obviously y1 minus y1 bar, y2 minus y2 bar, and subsequently you will get the other values as well. So those are the deviations that are mentioned over here. At this point, that relation is true, because that is the expression of the straight line. So if you put x2 over here, you will obtain y2 bar. So that is the value of y2 bar. How far is it from the value y2? That would be y2 minus y2 bar, and that is the error or deviation. That's what has been tabulated over here. We can write it in the form di, which is equal to yi minus yi bar. This is a bar over there. I do not know why it has become so small, but this is yi minus yi bar for I varying from 1 to 5 in this case. Now this approximating function, what is the approximating function? Obviously y bar equal to fx, that is the approximating function, in this case this straight line. It has to be chosen in such a way that the di's are small. If you can ensure that, then only you can say that it is a best fit curve. So what could be the form of this, say, error or deviation? The possible functions of the errors which may be considered for minimization. Here we are considering a minimization problem. We have some error, we want to minimize that error. But there are possibilities, different possibilities for this error function. One we have already shown you in the previous slide. In the previous slide, di is represented as yi minus yi bar. That is a straightforward consideration for the error. But there may be other possibilities as well. Let us have a look at some different possible error functions or deviation functions that can be considered. One such function is what we have already told you about, that is minimizing the value of the sum of these errors. So what we are trying to do here is that we have all the deviations, the di's given by yi minus yi bar, that is given, that is fixed. And we are considering the sum. So the total error that is there, that we are going to consider. So we'll add up all these values, d1 plus d2 plus d3 plus d4 plus d5. And for a straight line which gives the minimum value of this summation of errors, that is going to be considered as the best fit curve. Now there is a problem here. Can you identify the problem?
স্যার এই রেঞ্জটা পাবো না, মানে কতটার আর কি মিনিমাইজেশনটা হবে সেটা কি বলতে পারবো না সেটাই?
Here you have errors associated with, or deviations, DIs, for different points, starting with 1 going up to n. I can get those deviations because I know what is the approximating function, y bar. Y bar is given to me, say, in the form of this expression. Obviously, there would be combinations of A0 and A1, and that would mean probably infinite number of possible lines in this domain, in this XY plane. So which amongst those is the best fit? Which gives us the best result? That is what we are trying to find out. And what I am saying is that we will consider that curve as the best fit, which gives a minimum of some of the errors, some of the deviations. So we consider all those lines. Out of them, whichever shows minimum of this sum, D1 plus D2 plus D3 plus D4 plus D5, that is going to be the best fit line. It is obviously one of the possible answers, but it has got a problem. Suppose we have a very large positive error, and we have, for one of the points, one of the other points, a very large negative error. And coincidentally, the magnitudes of this positive and the negative error are almost equal. So they will cancel each other out. And as a result, you will get a false sense that maybe there is a very small amount of error which is present in this line. So large deviations which are equal but of opposite sign can cancel one another. So this might go or lead to some misleading answers. And that is not a good consideration for the error minimization function. Another possible function of the errors which may be considered for minimization is consider only the magnitude. We had a problem with the sign. So large positive error cancels out large negative error, gives a false sense that there is small amount of error. So let us not consider the sign at all. What we can do is we can only consider the magnitude, drop the sign. So again, we have a large number of possibilities. Out of that, whichever one shows the minimum value for D1 plus D2 plus D3 plus D4 plus D5. But this time, not considering the sign of the error. It does not matter whether it is a positive error. Suppose D3, this one, can be considered as a positive error. Whereas D2, as the point is below the line, may be considered as a negative error. Or it might be vice versa. You can change it around as well and call D3 as the negative error and D2 as the positive error. Whatever that may be, but here, that sign is of no consequence. What we are considering is only the magnitude. D1, D2, D3, D4, and D5, irrespective of their signs. So if you add them up, and for all of these possible fitted curves, make a survey through all of them, find out the one which shows the minimum of this sum of the magnitudes. That is one possibility to consider for the function. And it is a reasonable metric. It can be done. But the problem lies in the derivation of the analytical formula. It is difficult to derive the analytical formula. So it is not preferred that much. Another way of considering this minimization of error is just consider the maximum error for the different straight lines, different fitted curves. I will look at D1, D2, D3, D4, D5, and out of them, whichever is maximum, I will only consider that value. Not only that, I will also consider a predefined tolerance, error tolerance, capital T. And if that maximum of those deviations, DIs, is less than or equal to that predefined tolerance, then I will say that this is an acceptable straight line as the best fitted curve, best fitted straight line. This is in fact known as the Chebyshev approximation. For this one as well, it is difficult to obtain an algorithm. An algorithm for such approximations are difficult to derive. Keeping that in mind, we also discard this Chebyshev approximation. Moving forward, let us look at another possibility. We will consider minimization of sum of squares of the deviations. So what we are doing here, the deviations are the same. Deviations are, the DIs are of course yi minus yi bar. That remains same. But what we will consider is di square. So square of this term. And not only that, we will consider a summation of that. And means we will sum up all the squares of the deviations. So yi minus yi bar, and this is going to be squared. That is what is shown over here. So what is the advantage? The advantage is, of course, the errors of opposite sign do not cancel out because we are squaring them. So they become positive. And there is no problem of error cancellation. There are also other advantages as well. This sort of a function weighs large errors more than small errors. That means that there is sort of a penalty. If there is a large amount of error, you square it, it increases in amount. So this sort of acts as a magnification for large errors and prefers smaller amount of errors. And finally, the mathematics involved here are relatively simpler. Methods of calculus can be quite easily applied to derive the approximating functions analytically. So that is why this sort of error minimization technique, that is consideration of sum of squares of the deviations, is quite popular. And this is what we are going to consider for the best fit curve in our case. This is known as the least square technique. So what is the objective of this least square technique? Fitting a function fx, by the way, that is linear in this case. It may not be linear, and we'll consider nonlinear situations later on also. So the objective is to fit a function fx to the tabulated values, which minimizes the sum of squares of the deviations. And that is why this is known as the least square fit. So basically, we are considering this area, summation of this area. You have the deviations, D1, D2, D3, etc. Square means you consider these different squares. These areas, square areas, represent the square of the error. Summation means how much total area you are considering. If you add up all of this, probably you are going to have some kind of a total area like this. Let's say A1. Consider a second line, a different line. For that, maybe you get an area something like this. That is A2. That is summation of the area. And that summation of the areas represent the total error, square of the errors. So whichever line, again, there would be infinitely many possibilities of lines in this domain, in this plane. And whichever line shows the smallest amount of area, that is going to be the best fit curve. So the equation of the line, straight line, is y bar equal to a0 plus a1 xi. This equation is for this straight line. Here, a0 and a1 are, of course, constants. They are called the parameters of the linear regression model. So a0 and a1 are the parameters, also known as regression coefficients. And we know that what they physically represent. A0 is basically the intercept over here. That is A0, intercept from the y-axis. And what is A1? That is the slope of the straight line. So those are the physical interpretations of the two parameters A0 and A1. And our objective now is to find out a suitable value for A0 and A1 that represents the best fit line through these points. As you can see here, it says that the task now is to find out the values for the variables A0 and A1 that leads to the best fit straight line, which minimizes the sum of squares of the deviations. So, mathematically speaking, we are looking at summation of di squares. So, I varies from 1 to n di square. That quantity is represented by SR, that is the, you can say, deviations or errors, or sometimes this is also called residuals. Sum of the squares of the residuals is represented by SR. Di, as we know, is yi minus yi bar that we have substituted over here, and yi bar is represented by a0 plus a1 xi, and that is what has been substituted here. That is yi. So SR has got an expression like this. Now what we have to do? Mathematically speaking, we have to minimize this SR. So we have to find out the minimum of this summation I equal to 1 to n yi minus a0 minus a1 xi whole square. Let us now just go for a small demonstration. I'll try to demonstrate this problem graphically, and then we'll see mathematically or analytically how we can determine a0 and a1, which gives us the minimum value of SR. Let's see if it opens up. Yeah, okay. So here you can see the x-axis and the y-axis, And what I will do is I'll just simply bring in some points, quite arbitrarily, of course, like this.
Sir, what is this software, sir, you are using now?
This is a you can say it's an HTML page. It's a web page. I'll share with you the link. I will share with you. Okay.
Oh.
So let's say these are the different points that are present in the XY plane. You can get other points also, but let's not make it cluttered. And I want to fit a straight line through these set of points. The straight line is, of course, represented by this equation y equal to ax plus b. In our case, we had a0 plus a1x. So that means here b is equal to a0 and a is equal to a1 in our case. So right now, both these values a and b are 0. So you can see a line which is here collinear with the x-axis. If I increase b, that is the intercept, you can see how the line changes like this. I can also change the slope by changing this slider. And you can see the current value of these two constants here in this box. What about the error? The error is quite large over here. You can see for this particular line, we have errors such as these. These are quite large errors. I can also look at the squared residuals. You can see it's a very, very large value because these are going to be squared. And this is obviously not the best fit line. But I can change this. I can move this line up and you can see that the errors are changing. Here, you can see also this sum. If I move this, you can see that the sum is also changing. I can change the slope as well. You can see it coming down. So like this, I can experiment and try to find out what could be a best fit curve through these points. Probably something like this. I'm doing this by eye estimation. So maybe something like this would be obtained. So you can see compared to the previous values, obviously, if you add up these areas, that would be much, much smaller than what we had previously. So this is what we are doing in case of the least square fit. We are trying to find out a straight line. By that, I mean we are trying to find out these two constants that will define uniquely a straight line, which gives us the least amount of summation of squares. In fact, if you come here and click this, that is the best fit line that we can obtain. This one I had done through eye estimation. So obviously there might be some errors over here. So probably something like this. So I think you get the idea what needs to be done. I switch this off. You have a line which goes like this. It has value of a, that is slope of 0.87 and an intercept on the y-axis of 2.14. So this is the unique line that comes out of the least square fit. And you can see here that the sum of the squared residuals is so much less here. So almost close to 0. Obviously not 0, but close to 0. If I put a point over here, obviously it is going to change again. And now if we go for the best fit curve, that will somehow change like this. So you can try with different sort of points over here, and it will give you some idea about uh, what actually we are trying to do. What is the final objective? We are trying to find out an unique line that passes through all the given discrete data points, and that minimizes the square sum of the squares of the errors or deviations. That is what is done in the least square fit method. Is the demonstration clear? Any questions from there?
Yes, sir.
Okay.
Yeah.
Now let's look at the mathematics. So SR is a function of two unknown variables, A0 and A1. I want to find out the values of A0 and A1. Probably in the class 2 level, class 11, 12, you have gone through minimization problems or minimization maximization problems. So what do? We take a derivative of the function, put it to 0, and then try to find out the value for the variable, which will minimize that function. Here, because it is a function of two variables, we have to go for partial differentiation or partial derivatives of SR. And these partial derivatives would be taken with respect to A0 and A1. So we take partial derivatives of SR first with respect to A0, set it equal to 0, and then we again take partial derivative of SR with respect to A1 and set it to 0. So this is what is done. We have partially differentiated SR with respect to A0. So what will happen? This 2, that is a square term, that will directly come over here, and you have the summation I equal to 1 to n. This will be represented exactly as it is. So yi minus a0 minus a1 xi. And now each of the individual terms need to be differentiated with respect to a0. So with respect to a0, this yi and a1 xi are constants. There is no a0 term in them. So they will directly go to 0. But what about this term? This is minus a0. So differentiated with respect to a0 gives us minus 1. Similarly, the expression SR would again be partially differentiated with respect to A1. And that would give us this second equation, this equation. Now here you see that there is a term minus A1 xi. So if I differentiate it with respect to A1, this A1 goes away. What we are left with is this xi, that is minus xi. We can simplify this and we obtain the following two expressions. If you look at the second term in the first expression, summation of I equal to 1 to n a0. So this is nothing but a0 added n times over. So a0 plus a0 n number of times. So that basically is nothing but n into a0. We can replace it over here and get an expression like this. So n a0 plus a1 summation of I equal to 1 to n xi equal to summation I equal to 1 to n yi. The second expression can also be written in this form. So what we have here, we have two equations in two unknowns. The unknowns are a0 and a1. The coefficients of a0 and a1 are all known. N is the number of data points. You already know that. The data points themselves are known. So xi, yi are known from 1 to n. So you can calculate these summations very easy. And once those summations are calculated, what you have is basically a set of linear simultaneous equations which can be pretty easily solved. If you solve for them, these are the two expressions for A0 and A1. I'm not going to explain them in detail because this is basic algebra and you can probably find out these expressions by yourself. But one thing that should be explained here is that the first equation can also be written in this modified form. So we have taken this A0 on the left hand side. On the right hand side, you have the rest of the terms, and we have divided both sides with n. What about these two terms? This is summation I equal to 1 to n yi divided by n. And this is summation I equal to 1 to n xi divided by n. What do these two terms represent? Can you tell me?
It's a normal mean by AM, arithmetic mean.
Average. Simple average. Average of the values of x, average of the values of y. So I can write them as A0 equal to ym minus A1 xm, where xm and ym are the mean of x and y data respectively. So it points to a very important, you can say, point regarding the linear least square fit, that the linear least square fit line always passes through the mean of the data points. This is the equation of the line, the best fit or the linear least square fit line. And you can see that ym is equal to A0 plus A1 xm. What is ym and xm? They are the mean of x and y data. So it obviously means that this line will always pass through the mean of the data points that are given. So it's a very important result. Now let's talk about the algorithm. The algorithm for developing a C program that gives us the best fit line through least square method. We have the given data on one side. So the first task would be to read the input. In reading the input, you must know how many data points are present there, whether it's 10 number of data points or 50 or 100. So you have to ask for a specific n value, that is number of data points. And once that is given, then you can formulate a for loop which varies from 1 to n with steps of 1 and read the values xi and y. So basically what you need to do is define an array x n, or you might write xin yi, while declaring these arrays of variables, you might go for some value of 100 here, like that. But that also indicates to a fine point that you need to keep track of what n is being provided by the user. If this n becomes greater than 100, then obviously you have a problem. It is going to be out of bounds. So you might want to think about installing a check to see whether this input value of n is actually acceptable or not in terms of the array size. And our objective is to get the value of A0 and A1. We know the expressions of A0 and A1, although it looks quite complicated with the use of all these summations, but the expressions in fact are very simple, because all of these x's and y's are completely known, as is this n, these n's. So this is basically a very simple algebraic relation. And how do we go about finding out these summations? First of all, we need to declare these variables, these 4 variables, and initialize them to 0. Now, why these 4 variables? You have some x, some x sq, some y, some xy. If you scan through these expressions, you will find that there is summation xi square, which is some x sq, summation yi, that's here, summation xiyi, that's there, and also you have summation xi here and here as well. So that is taken care of by this variable. So in total, 4 different summations need to be evaluated. How do we evaluate them? In fact, this is quite simple. You take a for loop with steps of 1 going from 1 to n, and write down this expression, that is sum x is equal to sum x plus xi. So this is an assignment statement where at the first step sum x is 0. This is 0 value at the first step. That means when I is equal to 1, we have initialized sum x as equal to 0. So when it comes here, it will be 0 plus x1. So the value of x1 is now stored inside sum x. When it goes for the next iteration, I equal to 2, then sum x will be added with x2. x1 was already there. Now x2 is added to it. So sum x now contains x1 plus x2. When it goes for the third iteration, x3 will be added. So like that, at the end of n steps, inside sum x, you will have the quantity x1 plus x2 going up to xn. Similarly, for the other ones, other summations, also you need to evaluate these things. So this for loop will take care of all the summations. Once the summations are done, you end the for loop and go out of it. After that, only thing that remains to be done is evaluation of A0 and A1. How we can do that? First of all, calculate the denominator. These summations are already calculated. So you have the expression here in the denominator. You just simply calculate that. One thing to be noted here is that there is a summation of xi square. That means this is x1 square plus x2 square plus x3 square going up to xn square. This is certainly different. This is summation of I equal to 1 to n xi. That means this is x1 plus x2 plus x3 going up to xn, and then whole square. So there is a subtle difference between the two terms here. Do not confuse that. So once you have got the denominator, then you can simply calculate A0 and A1 as per the expressions given there. Write down the values of A0 and A1 that is displayed on the screen and bring the program to a stop. So it's a very simple program that you can very easily develop for linear regression. And I would ask you to do this linear regression uh, by yourself as a sort of practice. Try to develop the C program following the algorithm that was shown here. That is all about linear regression. But we also have quadratic or higher order regressions as well. In general, it may be necessary to fit a higher order polynomial instead of a straight line, depending on the application, depending on what kind of problem you are solving. And a polynomial of a specific order can be fitted through a given set of data points, satisfying the same minimum mean square error criteria. The fundamental remains the same. What is different is the approximating curve that we are considering. Previously, we had considered a straight line. So y bar was a0 plus a1x. So it's a straight line. But now we will be considering other type of curves or higher order curves. The value data points remain the same. So let's look at a specific example. Quadratic least square fit. The fitted curve is to be of the quadratic form. We can write it like this. Previously, as I mentioned, it was a0 plus a1x. Now we have added this extra term, the quadratic term, and that makes it a higher order regression. We have a nonlinear x term, and of course, it's a quadratic regression. So in terms of yi bar, it can be written like this. So a0 plus a1xi plus a2xi square. And you can probably guess what is going to be the sum of the squares of the deviations or errors. The expression is same, this expression. That is absolutely the same thing that we have considered. What is different is this, yi bar. Previously, it was only a0 plus a1x. Now, this is a0 plus a1xi plus a2xi square. That's what you can see here. After this also, everything remains same. That you will have to partially differentiate this SR, equate the value to 0 in order to get a set of linear simultaneous equations. Only thing different here is that now you have 3 linear equations and 3 unknowns. That is because you obviously have a0, a1, and a2. So while partially differentiating SR, you will need to do 3 partial differentiations. One with respect to a0, one with respect to a1, and the third one with respect to a2. All of these 3 partial differentiations would be equated to 0, and that would give the normal equations for the quadratic regression. These linear simultaneous equations can be solved to find out the regression coefficients a0, a1, and a2. So again, I repeat that the basic principles, the fundamentals remain absolutely the same. The only thing that changes is the approximating function. You can also consider other approximating functions as well. For example, if we consider an mth degree polynomial, the same basic idea can be extended to that as well. The given set of n data points remains same, but now what we are doing is fitting this mth degree polynomial instead of the quadratic polynomial. This is much more a general thing to consider, and as already mentioned, the mathematical technique remains the same. Only thing that changes is the approximating polynomial, and depending on that, what would be the number of coefficients, regression coefficients. So we have the expression for SR. You can again see that this is the same expression as we had previously. The difference lies in the consideration of yi bar. You can see that it has been now replaced with the mth order polynomial that we considered here. This one. So after that, we have to partially differentiate SR now with respect to m number of coefficients. So A0, A1, A2 going up to AM. So with respect to A0, A1, A2, AM respectively, and setting each of them individually to 0. So how many number of equations we obtain here? We start with A0 and with AM. So from 0 to M means M plus 1 number of unknowns are present. There would be M plus 1 number of linear equations. So this is the generalized form of the least square fit method. Linear simultaneous equations can be solved to obtain the regression coefficients A0 up to AM. How do we solve them? In a later class, we will look at these equations through Gaussian elimination, that is a direct method. There may be other indirect or iterative methods as well. So if you can develop a program for this general approach to the regression problem, and you can link it up to a module for Gaussian elimination, then the whole process may be done through or implemented through the C program. You do not have to do anything by hand. So that is the advantage of computer implementation of both the regression, general form of the regression, and Gaussian elimination. We have already extensively seen what this regression technique is, and more specifically the least square technique is. And later on, we will concentrate on Gaussian elimination. But before we end today's class, I should also acknowledge that there are other nonlinear models for using least square fitting. Such models would be maybe exponential, where y bar is given by a to the power minus bx, or it could be in the power law form, where y bar is given by ax to the power b, or it could be in logarithmic form, where y bar is given by a plus b multiplied by natural logarithm of x. So these are possible models for consideration in case of least square fitting. But here again, I would mention that the expressions remain the same. What has changed only is the y bar value. We can consider different sort of y bar values like these, and they can be input over here, and you get an expression for SR. The next part is also same. You partially differentiate SR with respect to the coefficients, however many coefficients there may be. In these three examples, there are two coefficients, A and B. And after partially differentiating SR with respect to these coefficients, you set them to 0 to obtain a set of equations. But do note that here, the set of equations that are to be solved they may not be linear. What you obtain in the end may be a case of a series of simultaneous non-linear equations, which might be just a little bit tricky to solve. But then again, you have already seen certain techniques for solution of non-linear equations. Those can be adopted to solve for a series or a system of non-linear equations. We have previously seen how to solve a single non-linear equation, and that can be extended, of course, to uh, a series of nonlinear equations. Solution techniques can be developed for a series of nonlinear equations. But in the end, I would mention that because we do not like to deal with nonlinear equations too much because of certain difficulties in implementing solutions, the general polynomial method or consideration of mth degree polynomials to fit against a set of n data points, that is why they are so popular. In most cases, we consider the polynomial form. So that brings us to the end of today's lecture. Thank you. Any questions?
স্যার কি করে বুঝবো কখন মানে কোন মডেলটা ইউজ করব, কখন লিনিয়ার করব, কখন লিস্ট?
Yes, sir. Same question, sir.
Very good question. When do we know
প্লটটা দেখতে পারবেন?
when do we know that we should go for a linear regression or a non-linear regression? And if we go for a non-linear regression, what should be the order of the polynomial? Should we consider m equal to 3 or m equal to 5 or m equal to 100? That's generally what your question is, right?
স্যার
What we can do is we can create a generalized program for this entire module. So what can be done? First of all, you start with m equal to 1. So that means y bar is equal to a0 plus a1 x. So that is what is meant by m equal to 1. So for this, after you do the partial differentiation and setting it to 0, you will get expressions for a0 and a1. We have seen the algorithm just now. So from there, you will get a value of a0 and a1. And from there, you will also get a value for the final minimized error. With that value of a0 and a1, what would be the value of SR? That also can be calculated. And once you have done that, then you go back to the beginning of the problem, start of the problem. Now you say m equal to 2. Now a0 plus a1 x plus a2 x squared. Do the calculations, same thing, get the coefficients, expressions for a0, a1, a2. Solve it. You can get again another value of SR. So like that, you just continue maybe up to m equal to 5. So we started with m equal to 1, 1, 2, 3, 4, 5. 5 different situations you consider. And out of them, see which one gives you the least amount of SR. That would be the that would be the answer to your questions. That is the curve which will give you the best fit among the best fits. Linear, quadratic, m equal to 3, 4, and 5. Now here now comes the question that for m equal to 4 and 5, it's very difficult to solve by hand and get the expression for A0 and A1 and A2 and A4, A3 like that. So you will have to solve linear simultaneous equations of say fifth order. You do not need to. You can link this module for least square technique to the maybe Gaussian elimination technique. Gaussian elimination technique that we'll cover in the class will be a generalized one. So you can develop a program for say n number of equations, n number of linear simultaneous equations. So now, once you link these two up, then there is no need for solving anything by hand. You do not have to do any calculations. In the first part, you will do up to only the partial differentiation and obtaining of the coefficients of A0, A1, and so on, Am. Once you obtain the coefficients of that, the next part would be taken care of by the Gaussian elimination programming module. And that will, in the end, give you the values of A0, A1, A2, like that up to An. So this is one of the ways by which you can find out that out of the linear, quadratic, and higher order fits, which one is the most appropriate, which one gives you the least amount of residual error. Is that clear?
Yes.
Probably when we do the Gaussian elimination technique and other associated techniques, it will become much more clear. Any other questions?
ইন্টারপোলেশনের সময় মানে আপনি ওই পেজটা বলতে পারবেন স্যার ইন্টারপোলেশন?
Interpolation. Okay. Let's go to interpolation. Here.
হ্যাঁ
This
স্যার
page?
বলছি শোন, ওই x3 আর y3 আর x4 y4 যদি আমি কার্ভটা ওই দুটো পয়েন্টে একটা প্যারাবোলিক কার্ভ পাস করে, তখন তো y এর মানে এররটা অনেক বেশি হয়ে যাবে স্যার। তো
হতে পারে নিশ্চয়ই হতে পারে। তুমি বলতে চাইছো এখানে আমি x3 y3 এখান দিয়ে একটা প্যারাবোলিক কার্ভ টানলাম, আবার সেম আমি x2 y2 x3 y3 x4 y4 এটা দিয়েও একটা প্যারাবোলিক কার্ভ টানতে পারি।
হ্যাঁ,
তাই তো, দুটোর ক্ষেত্রে রেজাল্ট সেম হবে না, দুটোর ক্ষেত্রে রেজাল্ট আলাদা হবে।
মানে যাই হোক ওই y পয়েন্টটা ওই কার্ভটার উপরেই হবে,
y পয়েন্টটা ওই কার্ভের উপরই আসবে।
মানে ওটাই তো মেইন ডিফারেন্সটা স্যার এই দুটো।
Yes. Interpolation we'll do in the next class. I'll show you examples also. Okay. So just wait for that. Okay. So if there are no more questions, I'll end the class here. But tomorrow there won't be any CAD classes. Is it right?
Sir, we didn't get the notice of holiday, but
No, holiday has been declared. I have the notice.
okay, sir.
6th is a holiday, and your puja vacation starts from 11th.
Yes.
11th to 22nd.
স্যার আমার না বৃহস্পতি